The three sections from this test are all similar in nature, similar in formulas, similar in ideas, and they're related. So, what we're going to do,
It's out of 50?
I don't know, I haven't made it yet. What we're going to do is we're going to take a look at the relationships that exist amongst these formulas, and we're going to see that they're similar in nature.
So these are the sections on the problem set?
Yes. Same as always, yeah. It's whatever we did before the test. Now, in 17.2, I'm going to start with formulas and mathematical. And we'll talk about conceptual stuff as we go through it. But I'll tell you now, as far as expectations are concerned, I would say maybe like 5 multiple choice, not like 10 this time, because there's not a lot of conceptual on this test. Probably like 3 or 4 short answer in the middle, and then the rest mathematical. So the test is probably going to be like 50 points. I don't know. Honestly haven't finished making it yet. Now, my guess would be that the math part would probably be almost 25 points out of the 50 points. Okay? Opposite of the last test where the math part was only like, I think 12 points out of 50. So anyway, just to give you a little heads up. 17.2 was electric force. Okay, there's a huge difference between electric force and electric field and electric potential energy. These are all different terms. So electric force, Fe equals KCQ1 Q2 over R squared. I put the little E here for electric force. Now, Kc is always given in any formula. It's Coulomb's constant. It's on your formula sheet. 9 times 10 to the 9 Newton meters squared for Coulomb squared. You never need to memorize that. What is R? What is R in these 3 equations? No, not your radius. The distance between the 2 particles in this case, or with an electric field, the distance from the source, or with electric potential energy, the distance between the source and the other particle. But R in these formulas is going to be distance. What about Q1 and Q2 in this formula? We'll talk about 17.3 in a minute. For electric force, Q1 and Q2, what are they? Sarah?
Charges?
Yeah, the charges on the 2 particles. The charges on the 2 particles. Now, conceptual kind of questions you could expect from a formula like this. We talked about repulsive and attractive forces, understanding the difference. When you have like charges, they repel. Opposite charges seem to attract. When we talk about the Q1 and Q2 value being analogous to the mass. If you think back, this formula is analogous to our gravitational formula. Okay, we can see how these formulas are very similar. So Q1 and Q2 are charges of the particles, but they're just material properties. Okay, they're a property of the particle, just like mass would be a property of the particle.
Sorry, you were saying R is the distance between the 2 particles?
Yep. So we see this analogous nature between these 2. We're also going to see it in 18.1, which we talked about, with Q times E times D being like mgy for potential energy. So it's not going to be something where it's going to go away. You have to understand that in physics, formulas are similar, although they're completely different applications. What else? Conceptually, what if like it says both charges double, or both charges triple, or the distance between them halves, or the distance between them doubles? Those kinds of questions, definitely expect those. Okay? So let's do one of those. Let's practice one of those together. Let's say the charges on both particles quadruple. The charges on both particles quadruple, and the distance between them doubles. The charges on both particles quadruple, while the distance between them doubles. Determine the net effect on the force as a result. Charges on both particles quadruple, while the distance between them doubles. Find the effect on the net force or the electric force. So if the charges both quadruple, how would I rewrite my FE equation? If the charges both quadruple, start with that.
16 times AC Q1.
Yeah, now the 16 comes from this, right? Just so we're all clear. If both charges quadruple, that's really what you do. And Sarah said, well, 4 times 4 is clearly 16, so just say 16. I agree. All right, so that's what I would start with so far. The denominator, though, has to change as well. Kian?
Oh, actually, yeah, you just put it through.
Yeah, good. Because of what happens to the distance between them. It doubles. Now, the 2 there is not just 2r, it's 2r squared. So the denominator becomes, there's a 4 in the denominator now.
So, I'm sorry, how did you phrase the question again?
Determine the change, or if the charges both quadruple and the distance between them doubles, find the net change on the force. So that's what it looks like. Sarah pulled out, or talked about the 16. Kian told us about the 2r quantity squared, which becomes 4r squared. 16 over 4 is clearly 4. So if you were giving an answer as a verbal response as opposed to like a multiple choice, your verbal response would just say the force goes up by a factor of 4. Kian?
No, that's not it.
Are you sure?
Yeah.
What were you going to ask me? I'm curious now.
No, that's good.
Okay. So 16 over 4 reduces to 4, so you can clearly see that the only change in this, or the net change, would be a factor of 4. Can we close that window halfway, please? We have got these wide open, so close that halfway. No, leave these. These are fine. Those are like just a little bit open. I'd rather have that one closed. What is the big deal, Jack? What does it matter?
Nothing. It's just hot back here. Sweet Jim. Sweat.
I know. You don't want to be, sweating and cold at the same time. Cool off slowly. All right, let's look at 17.3 real quick. Look at the formula, go over conceptual example, and then we can get back to mathematical with the 17.2. 17.3. 17.3 was all about what? What was 17.3 all about?
Electric field.
Electric fields, not electric force. Again, 17.3 was about electric fields. What produces an electric field? What produces an electric field?
Source of positive and negative.
Good. Either a positive or negative source. That's why we only have a Q here. We don't have another Q in this formula simply because it's a source that's producing the field. The other particle that's in the field we can talk about in a moment, but for now, if we're trying to find out what the field is, we need to know what the source has as a charge. That's Q. R is the distance from the source. R is the distance from the source.
From the source to what? Because you don't have more than one.
Well, that's the question, really. So, in the problem, it might say find the electric field 2 meters from the source, 3 meters from the source. But then later on, you could follow up with another particle. And I'll go over that now, Sarah. Okay, so again, same general formula, but Q is now the source charge. There is no other particle right now. We'll talk about that in about 30 seconds. Okay? And R is the distance from the source. So if a problem said find the source produced, or find a field produced by a source of 17 microcoulombs at a distance of 2 centimeters. Well, this is 0.02. This is 17 times 10 to the negative 6 for microcoulombs. This is 9 times 10 to the 9. You literally just plug it in. It's a plug and chug. These are generally easier problems. Now, the follow-up part was what we did in the end of 17.3. And we talked about the electric force equaling the electric field times whatever the other particle is in the field. I think on your formula sheet, I write this as follows. I wrote it this way on your formula sheet. Okay? That's how I wrote it on your formula sheet to show you that it was force per unit charge. So the units on E, anybody remember what the units on capital E are?
Coulombs over meter?
What do you got?
Newtons over Coulomb?
Yeah, good, Julie. Newtons over Coulomb. How can you tell if you forget? Look at the top right formula. What are the units of force? What are the units of charge? So electric field must be newtons over coulombs. This might help you remember the units for big E. All right? Now, written this way, it's the same thing. You're just multiplying by Q0 on both sides. Okay, these formulas are identical. Now, if we know the electric field, let's say I told you there's a source of something. I said, at a certain distance of whatever, 20 centimeters. And let's say your electric field turns out to be 15 times, let me think reasonably. 6 over that. 15 times 10 to the negative 3 newtons per coulomb. Let's say that's what we get as a number, okay? If you know the electric field, right? If you know the electric field, and then suddenly it says there's I don't know. What's the molecule that's just 2 protons? What is that called? It's not helium. Helium is 2 protons, and you need electrons for helium. It's a diatomic molecule of hydrogen, right? So diatomic hydrogen. I don't know what it actually called. Imagine you had 2 protons in space, okay, clumped together, and the question was, how much force acts on those 2 protons in this field? Well, you have the field strength, E, that goes in right here. If you had 2 protons, what's the charge on 1 proton?
1.6 times 10 to the negative 19.
Yes, good memory. So 2 protons would be 2 times 1.6 times 10 to the negative 19.
And the protons are in space?
Yeah, so it's a molecule that is consisting of only 2 protons, okay, at a given distance from the source. So if we did have that scenario, it would be something like this. That would be 2 protons. If it were 2 electrons, what would change?
Negative 1.6.
Yeah, this would be a negative number, thus I would end up getting a negative force. Well, if I have a positive field, I have to have a positive source to start, which means that this came out to be positive to start the problem, giving us a positive field. A positive field with a positive proton or a positive charge would be repulsion. If this were negative, it would be attraction. So the negative positive just indicates attraction or repulsion there. But the concept here is that this formula here is again analogous to something we've seen. This is just like this. Not written this way, obviously. We wrote it as mg here and here, but it's the same thing. Capital E is the electric field. Little g is the gravitational field. Little q over there is the charge, Q0, the charge on the particle. M is the mass of the particle. So the formula that we use is again analogous. Every section of this test has an analogous formula from earlier in the year. The last one was Fg. This one is Fg equals Gm. The next one's going to be potential energy as the analogous formula.
The distance is always going to be positive, right? Even if it goes to the left. Okay.
Yes. And in this case, it wouldn't matter because it's squared, but yes, that is true. Okay. Let's go to 18.1. Go over the formula, go over the conceptual. So, by the way, conceptually for this, for fields and field lines, what's the kind of stuff you should know? What did we talk about with fields? What's one piece of info?
Like repulsion attraction, like plus times energy.
Good. How does that affect the fields? What do the fields look like as a result then? Do you remember? No?
Oh, you mean out to infinity and towards, so if it's positive, right, they go out, and if it's negative, they go in.
Good. Remember, if you want to know what the field would look like, imagine you had a proton in space. That's always the way to test it. If there was a proton in space with a positive source, the proton would want to move away from the source. So that's why we're drawing arrows away from the source. So always think about a proton in space. That's your test charge. A negative source would attract the proton. So when we draw a negative source, we traditionally draw arrows coming toward it. If there's a positive and a negative source in the same proximity, what will happen is the field will continue from one into the other. The field lines will become superimposed on one another. And we did an example of this where we found out the electric field midway between these two charged source, or these two sources, or these two particles. I saw a hand shoot up somewhere. Yeah.
How do you know how many arrows to draw?
You don't.
You just
All you know is it's relative. If I gave you 3 diagrams, the one with more arrows is a stronger field.
okay.
The one with less arrows is a weaker field.
All right.
Yep, you never really know. It's just a diagram, that's why. What else?
Wait.
Yeah.
And the arrows represent charges.
The arrows represent the way a proton would move
Oh.
in space. They're called field lines, and what they really mean is the path a proton would take if placed. So if a proton were placed here, right, it would travel along this path. This is very similar to what you guys did with the electric field hockey thing the other day. Remember those like paths? The particle was unless you changed it, which you could have, was a positive particle, and that would have moved along those field lines. That's how you set up your diagrams to see if you can like get into that goal or whatever that was. What else about 17.2? Anything else? 3. Thank you, Ken. 17.3. What else? Anything else?
Do we
Yeah.
have to memorize the general rules of for field lines?
The 4 things we mentioned?
Yeah, 3.
Yeah, I mean, one of them said, well, read them off to us.
Field lines can begin positive charges or at infinity and must end at negative charges or at
That's kind of what we drew there. Go ahead. Then what else?
the number of field lines from a charge is proportional to the magnitude of the charge.
That's what Julia asked. Yep, you should know that also.
And field lines from the same field cannot cross.
Yeah, I mean, that one is one that's also true, yeah. You should know that field lines cannot cross. You should definitely know your rules of field lines. 2 of them, though, we see in diagrams. The field line's not crossing. We can see that in the diagram, but it's not obvious. It's not obvious before looking at a diagram like this. All right, let's go to 18.1. Was electric potential energy. And our formula for this, Kc, Q1, Q2 over R. Again, very similar to the 17.2 formula, except it's not R squared. If you're curious, it's because what you're really doing is you're multiplying by meters. And if you remember, what were the units for force? Newtons. And then newtons times meter is joules. Okay, so think about it. How do you get rid of an R? Aren't you multiplying by a distance to get rid of it? It's like you're multiplying by R up here, and this was R squared. It's because of newtons times meters gives you joules. Now, back to the question itself. This is the electric potential energy associated with a particle that's at a given distance from a source. So if you want to call Q1 the source or Q2 the source, it doesn't matter. One of those two is the source. The other one is the particle. Again, Q1 could be your source, and then Q2 is somewhere in that field, and as a result, it experiences some sort of push or pull, or some sort of energy, desire to change energy from the potential part of it. But if you call Q1 the source, then Q2 is whatever the particle is in space, depending on what it is in this case. Proton, electron, 5 protons, 7 electrons, whatever it may be. A charged particle of 3 coulombs, it doesn't matter. Now, the formula that we're seeing here came from this formula. That's where it came from, really. Now, we substituted in class for big E. We substituted Kc Q over R squared, and he gave us this. But how is that upper right formula similar to a formula from earlier in the year? MGY. Q is a property of the particle. M is a property of the particle. E is the electric field. G has to do with the gravitational field. D is the distance from the source. Y is also the distance from the source being the Earth for gravitational potential energy earlier in the year. So although this is the formula you're going to use mathematically, This kind of stuff over here is conceptual. QED is like MGY.
Going back to like the last slide or whatever, Q always what exactly? Like I know
A point charge somewhere in the field.
Okay.
Sometimes they call it a test charge or point charge. It's one of your given pieces of information. So if you have like a particle or 2 protons, 2 times 1.6 times 10 to the negative 19 is Q0 in that case.
Okay.
Okay? Let's see what else. I'm trying to think of anything for this conceptually that we talked about.
We wouldn't be given Q0 in the question.
Say it one more time.
We would never get Q0 given to us in the question, right?
You never have Q0 given you. You might. I mean, like, the problem might have you calculate an electric field and then say find the force on that field for a proton. Well, and a proton is Q0 in that case. It depends on the problem. But yes, you could be given Q0 on the problem. Assuming you have a field. You need to have a field to work with Q0. Let's see what else. Let's look at some math now. Let's do some math problems for this. Okay, I'm trying to think of what else conceptually I could ask you about, but there's not too much more.
When do you multiply the charge of the particle by like a number? I know there was one problem in the homework, but I don't remember how it was. It was like you have to multiply 2, because you have 2 particles by 1.6 times 10 to negative 19.
Mm-hmm.
So that's when you have more than one particle.
Yes, if you know the charge on a particle, but you have multiple of those particles, just multiply by that many times, however many there are. 17.2, we did basic stuff, and then we did more complicated stuff. So, let's do the basic one real quick, but the complicated one is kind of embedded in that. So if you have 2 charges at a given distance, right? 4 microcoulombs and negative 5 microcoulomb. What kind of a force will we have here if they're opposite signs? Attractive force. Andrew, what formula am I going to use for this to find out that attractive force?
Fe equals Kc times Q1 times Q2 divided by R squared.
Now, as a result of this, we want to think about the fact that we're going to get a negative answer as a force. It just means that it's attractive when there's 2 particles. When there's 3 particles, we have to use a free body diagram, which we did. So, for 2 particles, do I need to go further? Can you plug in? Right? If you know the distance, let's assume the distance here is, I don't know, 20 centimeters. Right? So, point 2 as R, 4 times 10 to the negative 6 as Q1, negative 5 times 10 to the negative 6 as Q2, and then plug and chug. Yes?
You just said that since it's going to be attraction, it's going to be
A negative force, you're going to see.
So, even if it was 2 negative answers, it would be positive?
Yes, because that would be what kind of a force?
Repulsion.
Yes, very good.
What, that's 20 centimeters?
Yep.
So attractive is always negative, right?
For 2 particles, yes. For 3 particles, though, remember, it doesn't matter. It has to do with the free body diagram for 3 particles.
2 particles, attraction equals negative and repulsion equals positive.
Correct, exactly right, Jay. For 2 particles. Let's look at 3 particles now. This is where it got a little bit tricky. Let's use nanocoulombs this time.
And the mu is times negative 6.
Times 10 to the negative 6 is mu. This is nano, though, this time. So what is that?
9.
Good. Negative 9, obviously, right? So let's say this is our arrangement. How might a work problem like this be stated? Who could tell me what the problem would look like? What would it sound like to give me a diagram like this? This is something I realize that I feel like some of you need to work on a little bit. Draw yourself a diagram, then come up with a problem that would give you that. Dirks, give me a problem that would give you this diagram.
What is the total force felt on particle 2?
Okay. if, give me more, I need to know about because I'm giving you a diagram assuming from the problem, right? So what would you have to be given about dimensions and charges?
The distance from 2 to 3 is 3 meters, and from 2 to 1 is 1.5, and the charge is
Blah, blah, blah. Good, very good, Dirks. Okay, so that's what it would sound like. So expect the wording for the problem to be similar to the wording on your homework, on your problem set, on the example we did in class. You've done at least 3 of these by now. We did 1 of these in class together. We actually did, I think, another one, right, the day after. Didn't we do it again? Or it was a homework one I went over with you. And then you also should have done one of these for your problem set. Or you will if you haven't done it yet. So you can expect the wording to be similar to what we've seen. Now, as Dirks mentioned, the problem may state, find the force on particle 2. Find the force on particle 3. Find the force on particle 1. I will not ask you to do all 3 because of time, to be honest. I'll tell you that now. Okay, but you will have to find the force on one of these particles. James, pick 1, 2, or 3. 1. So if we want to find the force on particle 1, we start by drawing particle 1 by itself. Then we say to ourselves, I've tried explaining this differently lately because I think people are confused with the explanation. So here are the words now. Listen this way. I think it was this morning I was working with you on this. Think about this. If Q1 were able to move, which way would it move because of Q2? Again, just think about it. Don't answer yet. If Q1 could move, which way would it move because of particle 2? Kian? Not to the left, no.
Towards.
It's clearly to the right, the opposite, right? Why, though, Andrew? Give us a reason.
Because they're opposite charges.
Yeah. Kian, look up real quick. If Q2 could not move, and they're opposite charges, well, then Q1 has to be pulled toward it. So Q1 is being pulled toward Q2. It's a force, and again, remember I told you it doesn't matter, the subscript, which way you write it, as long as you are consistent. I'm writing it this way, so I would say it's a force from particle 2 on particle 1. Okay, a force from particle 2 on particle 1, to the right. Next, if Q1 could move, where or what direction would it move as a result of particle 3? No. So look at particle 3's charge.
I thought it could go, I thought if they were attracted and they were on opposite ends, it would like attract the other way.
They would both pull each other, but remember, assume that the one that you're looking at is the only one that can move.
Okay.
If these two particles cannot move, and this is a negative charge on the end over here, it's also going to pull Q1 this way. Again, assume the particle of interest can move and the others cannot. So as a result, we're going to have another, I'm going to make this nice and big, this particle here, so we can see these 2 lines. And we're going to call this 3-1. So both particles 2 and particle 3, particles 2 and 3, are pulling on particle 1 to the right.
Is that because they're both negative?
Exactly. They're both negative. Particle 1 is positive, so they're both pulling it to the right. Now, obviously, 2 and 3 are repelling each other, but we're not concerned about that right now. The question was, according to James, what's happening on particle 1? That's why we drew this way. Now, how would you find F31 and F32?
You would do F equals KC, Q3, Q1, and over R.
And let's use our absolute values here because we already took into account the negative signs. What's the R value between particles 1 and 3? 4.5. Again, particle 1 all the way to particle 3 is 4.5 meters. You got to recognize that.
I don't really understand the sense.
So this is the force from particle 3 acting on particle 1.
Oh,
The force from particle 2 acting on particle 1. How about F21? What's the difference there now? F21 will look like what? Summer.
KC Q2 Q1 over 1.5 squared.
Again, they're separated by 1.5 meters, which is why some are used 1.5. And then Q2, Q1, or Q1, Q2, it doesn't matter. Multiplication is commutative. Does not make a difference. Sarah.
When they use the absolute values,
Why or when?
when?
When you're doing this problem. Because, remember?
Free charges?
Yes, because the free body diagram already took into account whether the signs were negative or positive with repulsion and attraction. So if you tacked on the negative signs, it would completely screw the problem up because you'd be doing it like twice. Okay? So because of the free body diagram taking into account whether the signs are negative or positive, you do not need them in the mathematical component here.
So the answer is because there's 3.
No, when they're free, they're used. That's when. Why? Because there's free.
Why? Because we already took into account the negative sign in the diagram. Jack.
Just kind of like different from this, but like say Q1 was positive and Q2 is positive and like Q3 is still negative, would then you determine like which way it goes by which has the greater like numerical value?
Yes, and I'm gonna in a second I'm gonna let's see, can I do this? Would that work? No, they both go left.
Yeah.
Oh, for Q3 it would work. Let's look at Q3 in a moment. We'll do that. So as a result, you're gonna get F21, you're gonna get F31. Look at your free body diagram. You drew arrows which way? Both right. So they're both going to be positive. So if you get a number here of 5 newtons and a number here of 3 newtons, the answer is? Positive 8 newtons. Remember, with a free body diagram, if you're finding the net force acting on a particle, literally just add the forces together with the correct sign. If the force had been drawn this way, it's a negative sign. This way, it's a positive sign. Simple as that. Okay, you're not going to have to worry about your negative sign, again, once you draw your diagrams. Let's look at particle 3 and analyze it. You could definitely expect me to give you, well, not definitely, but you could expect a problem where I have you draw a free body diagram of all 3 and then not calculate it, because that's just a ton of work to sit there and calculate. Or maybe I'll have you draw the free body diagram for all 3 particles, and then find the net force on particle 1 at the end.
So just like that.
Okay? So like what we did, but also drawing the other free body diagrams, which we're going to do now. So let's look at the free body diagram of particle 3. If particle 3 could move, and particle 1 and 2 were stationary now, right? Now we switch it up. Which way would particle 2 move, particle 3 move, as a result of particle 2? Away. Why?
Because they're both negative.
Good. Q2 and Q3 are both negative. So if Q3 can move, it would be repelled. So it's got to be away or to the right. So we could say this. We could say this is a force. Just to be consistent with my subscripts, let me look. 3, 1, 2, 1, okay. This is a force acting on particle 3 from particle 2 to the right. F23. Again, a force from particle 2 acting on particle 3. Now, make believe particle 2 isn't there next. So cover this up if you have to, or just cover it up mentally. Which way would particle 3 move, if it could, if particle 1 were stationary now? Why? Yes, this is positive, this is negative, therefore this would be attracted toward it, so the arrow on our free body diagram will look like this now. The force from particle 1 on particle 3. So we've got the force from particle 2 on particle 3, and that's repulsive, so particle 3 moves to the right. The force on particle 1 from particle 3, vice versa, from particle 1 on particle 3. Since this is positive and this is negative, this one is going to be drawn toward it. So when you're identifying or isolating one of the particles, think about the way that particle individually would move. You're always going to have a balance of arrows. So the third particle, Q2 now. Let's isolate Q2. How would Q2 move as a result of Q1? Good. It would move towards it. A force, again, from particle 1 acting on particle 2. Yeah. This is now Q2, how would it move from Q1?
Okay, so Q is
Q1 is stationary now because we're looking at Q2 now, right? So Q2 is opposite side of Q1, so it would move toward it, so we draw an arrow to the left.
Okay.
We then go to the next one, and we say, okay, let's go over to here now. How would Q2 move as a result of Q3? Also to the left. Why, Jack? Exactly. This is negative. This is negative. If they're both negative, it's repulsive, and we're trying to figure out Q2. So we assume Q3 to be stationary. Q2 would have to move away from Q3. So we're going to have another arrow to the left up here, a force from particle 3 on particle 2.
Would you ask us a question just determining that?
I might ask you a question that says, draw the free body diagram for each particle.
And
Yeah.
how do you determine which number comes first in the end?
It doesn't matter as long as you're consistent. So see how I've been writing, every time I've been writing the particle of interest as the second one?
Yeah.
Like 3 was second there, 2 was second there, 1 was second here. Just be consistent. It does not matter which way. Okay?
Wait, so when you say balance arrows, all three, like when you do all three, like so the first one had 2 going left, the second one had 1, and then the third one had both right, so that's what you mean.
Exactly. It's always balanced. This one down here, they were both right. That one up here, they're both left. This one is right and left. Why? Because if you were to sum all these answers together at the end, you get 0. Equilibrium. Okay? Nothing is actually moving here. That's the thing. Nothing's physically actually moving yet. It's a question of where would it move? How would it move as a result? Okay? How would it move really? So Q2 would clearly move to the left. Q1 would clearly move to the right. What about Q3? Which way would Q3 move, Dirks? You had your hand up, right?
It would move to the left.
Why?
Because the force is greater.
How do you know? Because my arrow is bigger?
No, I'm just doing it with the number.
Oh, you're doing it quick in your head? Good. So, but if you didn't know, what would you say? It would move to the side that is greater.
Isn't Q negative 3 greater than negative 5?
Yeah.
Yeah, but the problem is the distance changes it also. So you can't assume that just because the charges change, okay? Like F13, for example, Jack, is a distance of 4.5. F23 is only a distance of 3. So not only the Q's changing, but R is also changing. So which is changing faster, and then R is squared. So to predict it would be almost not impossible, not by any means, but it would be very illogical to do that. What I would do is I would say this. If F13 is bigger than F23, it moves left. If F23 is bigger than F13, it moves right. This one is the one in question. This one is clearly moving left, and this one down here, if I can pull it up, is clearly moving to the right. All right, so this is the kind of question you could expect for 17.2 mathematical. Let's go to 17.3. We're going to run out of time, so I want to keep going. I know you had a question. I want to keep going for now. That was 17.2, electric force. See what I mean? How they're similar to each other? 17.3 had to do with this. That was 17.2. So 17.3, you remember, is finding the electric field a given distance from a source. So let's say that the source is 5 coulombs. And we're trying to find the field that exists 4 meters away. All we need to do is literally plug these in. So we can figure out what E is. 9 times 10 to the 9 times 5 coulombs over 4 squared. That would give us the electric field that exists. Now, remember though, if you have more than one source, we did this example in class, if you have more than one source, you have to use superposition to add them together. So if you have a positive source here and a negative source here, everything wants to move away from the positive source and toward the negative. So if you wanted to figure out the electric field at this location, assuming that this distance is 1 meter and this distance is 4 meters. And we can give the charges, make this one 5 protons and make this one 5 electrons. So positive 5 E for protons, negative 5e for electrons. If you want to find the electric field at this location, right here, well, you're going to have a field that's produced from this one. The distance away is 4 meters. That's going to be 4 here. The Q is going to be 5 times 1.6 times 10 to the negative 19. You're going to multiply by this number. Then you're going to have a field from this one also, this distance of 1 meter away. So this will change to a 1 now. Since they're both fields are to the right or away from this charge, you can add them together. Okay, you're going to add those two values together like we did in class. What if they're both positive? What if they're both positive? Positive over here wants the field to go that way. Positive over here wants the field to go that way. So they're going to be what? What are they going to be? Yeah, they're definitely repelling for sure. But what about the fields? What would you have to do if they're opposing each other instead of helping each other? Instead of adding them, subtract them. So if you're trying to find a field at a location that's given and both fields are directed to the right, just add them together. But in this case, if I change that to positive 5e like I showed you right here, imagine 5 protons here and 5 protons here. Well, now the field lines would look like this. So to find the field at this location, they'd be opposing fields. So as a result, you would want to subtract those two numbers, not add them together at that given location. Now, again, I went over this already, but recall this equation is also needed. All right, this is an equation that is useful when you have a single field. Not more than one field, but a single field, and you want to find the force on maybe a proton or on an electron. Hey, 18.1, study your notes and your homework for that, please. Okay, for 18.1.